There's no world out there, right? I mean, it's all constructed in our head, basically. If you ask a 5 or 6-year-old, which I've done this with my grandkid, and you ask them, where their thoughts come from, where they point in here.
How can this physical body or this brain give rise to that sense that even your 5-year-old grandchild has of self, right? It feels very mysterious. It is very wonderful, right?
Words are really good. They're better than grunts, but they still don't quite capture the nature of what it is of thought. So thought goes beyond language, I guess, seems clear.
Just like the little movie playing in our heads, obviously, right?
We have a picture on the retina, and we have this, right, and it's this movie playing, basically, and that's how we represent the world. And of course, that's complete nonsense, because who's watching the movie? I mean, who or what is doing the decoding? I mean, there are some people who would argue that, there isn't a decoder. It's all just a continuous loop between the environment and the brain, basically. Again, it comes to the issue of where's the decoder for that population, and how do we connect up the population story, which is what everyone talks about now, to this higher level issue of representation. But the pre-wiring in the system at this torus kind of, reflects the manifold of the cells that are available, and it's already there by day 10. So what that tells me, and I think what it tells the Mosers as well, is that some aspects of the way we represent the world are, the whole brain is a relational device. Everything the brain does is relational.
Hi, everyone. This is Andrea Hiott. You're listening to Love and Philosophy Beyond Dichotomy. This is a special Hippocampus Love episode with Lynn Nadel. If you've been following the research channel on YouTube or elsewhere, you've probably heard a few talks between Lynn and I. There have been, I guess, 3 public ones now. 4th one I'm going to publish soon. This was I don't know if this was the 2nd or the 3rd talk. This one is about representations. I haven't posted it as an audio podcast, so I wanted to go ahead and do that as a bonus. I also wanted to do it because I had a paper come out recently, which is about radical relation. It's about representations and the hippocampus and a lot of these ideas. And Lynn and I just did another talk together about a paper that's related to that. And I'm also going to be posting a piece where I try to explain that paper, and also this idea of cognition being a form of navigation, navigation being a form of cognition. And by the way, I'm not saying either of those things, although it does get confused as if I'm saying one or the other of those. I'm not. However, I am saying that they are the same process, and I'm saying something actually much more radical than you imagine if you try to dismiss it as, oh yeah, mind is like moving through a landscape. But you'll just have to watch the other video to really understand that, because it's hard to explain. It's all about holding paradox, exploring beyond dichotomy, and everything else that you've ever heard on any podcast here, because this is one huge document that I'm putting together that goes along with the book that's coming out next year, but also my thesis and quite a few other things that are in the works. So it will all become clear at some point. If you actually care about all of this, you can put the puzzle together. It's actually a big jigsaw puzzle, which you can put together if you really want to. If you want to look at every video and listen to every podcast and look at it through this document, you'll see that it kind of unfurls in a fractal way. But in any case, a big part of this is Lynn Nadel, John O'Keefe, the hippocampus as a cognitive map, and Edward Tolman, all these people that have to do with hippocampus research, which is just so important to me, and I'm just so grateful for them. And I love being able to talk to Lynn, whose story I tell in part in the book that's coming out next year, but also just all his research and his thinking and his collaborations. And he was in Trondheim, I think it's a year ago we had this conversation. He was giving some lectures in the Moser Lab. They were also having the big Neuroscience Awards there at the time, which I think he talks about. So this is about representations in the brain. There's this problem if you don't follow neuroscience, but this idea of what a representation is, just to put it in really general terms, when you have a thought, where is that thought? Is it a little form in your head? How do you find it? So we talk about that, and it's, of course, much more complicated than that. But in a way, it's also just that. We just want to know what a thought is and how to find it, and what a memory is and where it is, and if that is even a question that makes sense, frankly, when we think about this whole process that we're studying. Lynn and I talk about that. We kind of break apart this idea of representation in the brain. We look back at this really old class he taught on representation, and if you want to see the slides for that, there is a link in the show notes and you can download them. But just remember, they're like 10 years old. But still, they're about a lot of topics that people still talk about. We talk about cognitive maps and different brain parts and their functions and how all this kind of can work, and this coding and decoding. And these words all mean special things, but it'll just make sense on a general level too if you listen to it. We do talk about population coding and topographic maps and other sorts of brain activities, but if you don't know what all that means, you can ask Claude or someone, or you can just skip over it because it's really just a conversation trying to figure out some basic ideas about what's going on. How can we remember? How can we think? Why is it that even a 5-year-old understands this process and somehow has come to imagine that it's happening in the brain? I think it's happening in the whole body, and that half the reason kids think that is because we tell them it's happening in their head. But anyway, that's a whole other conversation. You'll hear Lynn and I talk about that a bit. Mostly we're just talking about the mysteries of what it is to have memory and be alive. And wow, isn't that exciting? I think it's just endlessly fascinating and wonderful that we're here. Although, of course, it's also hard and challenging. But let's leave it on a positive note today. And here's Lynn Nadel. I highly suggest you check out his papers if you're interested in learning more about the hippocampus. I'm sorry my voice is almost gone, but I leave you with a big hug today and a hippocampus.
And, I'm going to give a talk next week, probably on, sort of the early history of work on the hippocampus, kind of the background to the emergence of the cognitive map theory, kind of what the field was like in the 50s and 60s and 70s, and, how it all came about, how, from my perspective, all the pieces came together, so to speak, historically. Edward said, the students here, they don't know anything that happened before more than like 10 years ago, he said.
It's a long time ago when you're 20.
Yeah. So
years.
So last year I gave, three research talks here of one sort or another. But this year I don't have it.
3 in 1 year. You were there that much last year?
I were not in 1 month. I gave 3 over the course.
Oh, so one.
No, I think I gave 2. It doesn't matter. I gave
Yeah,
a couple of
a
talks.
bunch.
I gave my research talks. This year I don't have anything here to say about research specifically that I wanted to talk about. So this is going to be my presentation while I'm here. It's a history talk, which I'm
That's
working
great.
on. A lot of fun putting the pieces together and trying to reconstruct the causal chain.
Gosh, I'd
that
like to at
link
least
one-
read that if you don't publish it somewhere,
Yes.
because that's probably very interesting to see how you put that together.
Yeah. Well, so much of it flowed through Montreal and and
I
places.
know, we talked about it.
Yeah. Right.
And
Exactly.
yeah.
This is the history that I've been talking to you about. Anyway, so
Speaking of history, today we're going to try to talk about this really difficult word, representation, dare I even say it, in terms of cognitive neuroscience, though. So for all the people who might be thinking we mean it in other ways, because you can talk about representation in so many different ways, whether you're in art or philosophy or whatever. But we're going to talk about it a little bit philosophically, I think, but mostly through sort of cognitive neuroscience, right?
yeah.
So I guess I was thinking today, I just kind of play like the student instead of trying to pretend like I really understand all this, because I was looking at your class, which I was just trying to find. But yeah, in any case, there's a class you taught like a long time ago, right?
Yeah, it's like 10 years ago I gave that. Most of the stuff that's in there, hasn't changed.
Before we get into all that, let's start with just cognitive neuroscience like you do, because it's really interesting, right? And I think for people who are trying to follow this, like, why do we focus so much on the brain? And I think in those notes, you kind of start with, it's been that way forever, right? Why are we trying to provide a brain-based account of cognition? Is it really just like simple? We just feel like we're in our heads because all our sensory organs are so located there,
Yeah, I mean,
Or-
if you were to take a kind of a Barclay stance, and John actually did this at the dinner. He was being somewhat obstreperous. He said, there's no world out there, right? I mean, it's all constructed in our head, basically. And so, I mean, if you take that kind of a position, I mean, it's all inside our head. We're creating this whole external world, which may or may not match up to what's actually out there. I mean, who knows? It better match reasonably well, otherwise evolution would have, squashed us. But yeah, so I mean, it's inevitable that you think about how is it that we understand and comprehend the world so that we can behave, so that our behavior, which whatever one thinks about the notion of representation, it's hard to say that the brain has nothing to do with behavior, right? I mean, it's what makes us move. You go back to movement, right? So I mean, we move because our brain tells us to move, and we move the ways.
But we also have a body, and I mean, it's not disconnected from the body. So I guess it's just like you move into the mind-body problem. It's just this feeling we have, right? Of our experience of the world feels like in our head, doesn't it?
Yeah, absolutely. We can't get away from that. It seems to me, no matter what philosophical position we take. So with that, as a starting point, you have to think about, well, how does it come to be that the brain models, let's use that term, and represents the outside world in a useful way, so that it can guide our behavior going forward. There's really doesn't seem like there's any alternative to that position. So it's not, people think about, well, so how does the brain represent the world? How does it do that? There's no other way to think about, it strikes me as a scientist, there's no other way to think about behavior.
So if we just think of people coming to a kind of awareness of themselves, then you have this feeling like you're sort of in your head. And the representation there in that really early sense is just that we can sort of have these images of ourselves, or we can sort of hear our thoughts, right? And so that feels like it's some kind of, we're representing the world in our heads, right? In a very simplistic way.
If you ask a 5 or 6 year old, which I've done this with my grandkid, and you ask them, where their thoughts come from, where they point in here. It's not, I mean, they understand, it feels that way, exactly as you say. So but there's, okay, I mean, I can leave it at that, except to say that there's a couple of different facets of this representation problem. I mean, one of them is, how does it do it? And how does it, how do we represent the world, and how are those representations used? All the kind of mechanistic questions about it. But then there's the more complex question, which I certainly haven't made any progress on, which is, why does a particular kind of brain activity represent a particular thing? Why is it that, activity in neurons in the visual system actually represent visual phenomena? I mean, it's the consciousness hard problem, but it isn't just about consciousness. It's simply, how come certain forms of activity represent certain things? Kind of. That's the deep question, for me.
Right. Yeah. Well, I think it's like we all have this with becoming aware of our own thoughts in a way. They don't feel physical.
Absolutely, they don't feel physical.
So we're physical and we're experiencing them physically, but from that vantage point, it feels like something not as physical as, for example, just to touch the table and,
Right.
So your little 5-year-old grandchild, it's kind of
feeling about it. Yeah.
But so there's this mind-body problem of, how can this happen, right? How can this physical body or this brain give rise to that sense that even your 5-year-old grandchild has of self, right? It feels very mysterious. Mind, is it consciousness? All these words we use in so many weird ways. But when it comes to trying to study the brain, actually thinking about what is reality, so to speak. If we just, I don't know how you feel about this, but I think it's a very bodily experience of cognition and representing the world. Of course, the brain is paramount, but let's just say we're going to focus on the brain and how this mental experience arises, what the brain's role is in it. And then we bring in this world represents. So what we're trying to understand is different kinds of reality. Isn't that how you say it in your talk? Like, there's a kind of current reality right now where I'm having thoughts. And then there's this thing with memory, which is the fact that I know there was a reality yesterday, or that the States recently, now you're in Norway, and all of this. And then there's the future, which you talk about, prediction.
Right. The brain can do all of that, but of course, mostly we get to describe what we're thinking about in words. But we know from a variety of perspectives that the words we end up using, separate from words are a form of behavior, of course, but a very specific form of behavior, they never quite capture what it is we're thinking about. I mean, we get as close as we can, but anyone who's kind of thought introspectively or tried to think deeply introspectively knows that they have some thoughts and they're never quite successful. They're never 100% successful in getting exactly what it was they were thinking into words. Words are really good. They're better than grunts but they still don't quite capture the nature of what it is of thought. So thought goes beyond language, I guess, seems clear. There's good evidence for this. Actually, Nancy Kanwisher and Doris Sau talked about this in their Kavli talks. There's pretty clear evidence that that you can separate out language from thought. I mean, a lot of thought is language, but not all of it. So that means there's some deeper. So the representations that we have in the brain are not just words. There's no kind of lingua franca. There's no Fedorian. What's the language of thought then? It's not words. So the language of thought has something to do with this issue of representations. Anyway, I mean, I think the data certainly suggests that the two are not totally overlapping. And that, again, just points to there's somehow the brain is representing information in a way that is useful, that you can use to generate language, that you use to generate behavior. And it must match the world, close enough so that, you survive in the world and the species survives. So how does it do that? That's kind of the core question. So the earliest default was, well, let's look at vision. You say, okay, we know that an image of what's out there in the world, is kind of reflected upside down in the retina. Well, okay, that's it. Problem solved.
Just like the little movie playing in our heads, obviously,
right? We have a picture on the retina, and we have this and it's this movie playing basically, and that's how we represent the world. And of course, that's complete nonsense because who's watching the movie, right?
You have this infinite regress of a little person in your head watching multiple screens. Yeah.
But of course, people thought that for a long time. They actually thought, that was a plausible story, basically. And that's one of the reasons why for decades, maybe a century, people were all twisted up about the fact that the image is inverted on the retina. It was like, wow, this is a serious problem. How do we deal with the fact
How are we watching everything upside down all the time?
Like, you can find hundreds of papers probably, written trying to, address this, the really hard problem of the inverted retinal image and how the hell does the brain solve it? It's completely meaningless, of course, because there's nobody inside looking at the image on the retina. It's got nothing to do.
But we just take that for granted in a weird way for so long.
So that picture in the head kind of story that, I think there was called an idola or a simulacrum. I mean, there were words that people put, that the brain just creates a replica of what's out in the world inside your head. But it completely in the end becomes pointless because it is default, to the homunculus. You can't get away from it. That problem doesn't go away, by the way. No matter what theory you have, there's always a problem of a decoder. I mean, who or what is doing the decoding? If any, I mean, there are some people who would argue that, there isn't a decoder. It's all just a continuous loop between the environment and the brain, basically, and there isn't a single decoder. It's all just connected to, it's this that's the embodied coach, essentially. Everything you do is
immediate sort of coupling.
To the and there's immediate coupling, and you don't have to think about a decoder because it's all part of and by the way, that may not that may turn out to be a pretty good story in the end.
I think it's part of trying to figure it out, but it's also, that's kind of the question of representation in a weird way too, is because as you say, I think in those slides, or you've said in other work, we often make that same mistake that people were making for so long of thinking there's someone in the head, but we forget that we're the scientists looking at the data that we've just gotten from the brain. We forget that we're decoding it. That step gets taken out. It must be in the brain in the same way it's in this little image of a
Right.
screenshot or something that we've taken. The MRI or whatever we're looking at isn't actually in the head like that.
That's exactly right. I mean, so we as experimenters looking at, unit recordings or fMRI or, multi-unit recordings or these calcium or whatever we're looking at, and we connect up certain patterns of activity in the brain to certain behaviors, right? We just assume that those patterns, we see those patterns and we see the fact that they're connected to these things inside the head. How is that happening? Basically, I mean, the inside part of the head is not looking at the data the same way we are. We're seeing all the data,
Right.
more, right? Any given part of the brain is seeing only a fraction of the data, so to speak, that we can look at as experimenters. And we jump to conclusions as experimenters. Oh, well, you see this pattern of place cells firing, it means, such and such. Well, is there any part of the brain that actually can see that pattern of place cell firing in the same way we can see it and use it in the way that we think it's being used or not? Probably.
I mean, even using language to talk about it is weird because, of course, they can't observe it in the way that we do with our senses or something.
Right.
Maybe there's some kind of pattern sensitivity or something. I don't know. That could be said. But
what's happening now, it seems. I mean, that lecture kind of ended at the point where people were saying, well, look, the brain obviously represents information in some sort of a distributed code, a population code. That is generally, accepted. There may be rather unique exceptions where a particular cluster of cells, has a very unique function. And you can say a small number of cells, do the whole job. But mostly it's vast arrays of neurons in some population. What do we do with that at this point? I mean, again, it comes to the issue of where's the decoder for that population, and how do we connect up the population story, which is what everyone talks about now, to this higher level issue of representation. And that's what's happened in the last 10 years. So all the stuff that I didn't, that I now think I'm just not expert enough about, but which I hear a lot about here, and which I heard about in the Kavli talks, especially Doris Sau, it's about this. It's about the kind of structure of that population people talking about the geometry of the structure of that population and the possible
topography.
Yeah, et cetera, et cetera, et cetera. And that's kind of where the field is headed now. And that's outside my zone of comfort. That's why I said I don't know that I have a lot more to add now, because I'm sufficiently, I would say not sufficiently sophisticated, but I could say I'm not at all sophisticated mathematically to understand, the kind of stuff that is being done now that points out the kind of consistent geometric, and this is not clustering or topography in the way that one sees in the visual system. This is simply the kind of possible states that this multivectorial kind of collection of cells can take, that somehow serve as the way it represents, say, an object or something. Kenneth Harris was here just the other day. He gave a talk on what I would say was like representations in the visual cortex. And it was all about, the population code. And the bottom line of what you were saying was that the excitatory neurons, the population code in the excitatory neurons is very high dimensional and captures the specific features of the sensory input, of the visual input. The population code of the inhibitory cells is low dimensional and reflects kind of the context, or the modulation of and those two things kind of playing off each other. Based, you might want to check out Kenneth Harris's work on this stuff.
Yeah, I'm gonna write that down.
He's He's at UCL. So, in the folks here in Trondheim are kind of very much on the issue of the torus, that, the manifolds, right? So as I understand it, a manifold is all of the possible states that a representation can take. Let's say in the grid cell population, there are constraints on where in the state space that population can be, right? It can't be everywhere. It can only be on this torus because of the nature and the torus, which kind of constrains the possible states the population code can take, i.e., how it can represent whatever is representing. That shows up. What they're showing here now is that shows up by day 9 or 10 in the rat pop, before they're moving around in the world, before they've seen anything. Their eyes are still.
They haven't explored? There's been no.
They've had no experience yet, but the pre-wiring in the system at this torus kind of reflects the manifold of the cells that are available, and it's already there by day 10. So what that tells me, and I think what it tells the Mosers as well, is that some aspects of the way we represent the world are given, so to speak, prior to specific experience. Although specific experiences can subsequently influence the way this thing works, the kind of really pure Kant, you might say, the Kantian, the built-in structure, constrains the representation. And, that's where the grid cell kind of property comes from. It comes from whatever that constraint is that, kind of determines the possible state that the population can take, as a collection. I don't understand any of that stuff. I mean, I hear it, but I don't intuitions about what that tells us about how the brain represents. I mean, that's going to be a part of the answer to the story of how the brain represents. So it goes one step beyond this notion of a distributed code. I mean, so, to step back into that lecture, I mean, I went from talking about, the retina to talking about the topographic maps that one finds in the visual cortex. Again, it doesn't matter that, the input to V1 is arrayed topographically from a representational perspective, from a cognitive representational perspective. Again, nobody's looking at it, right? But the fact that it's done topographically has obvious computational advantages. I mean, things that are near each other may be part of the same object, for example, pixels, voxels in space, I mean, so to speak. I mean, there's some real advantages to having a topographic code to represent, especially the spatial aspect of things. You don't get this in the auditory cortex. You only get this in the visual cortex. You get this in somatosensory cortex and so on. You don't get it with olfaction. You don't get it with taste. You don't get it with audition, because it wouldn't serve the same purpose there. You're not talking about things that are nearby in space.
Let's define this a little bit, because this is a really interesting part of the history of trying to understand cognitive neuroscience in the way we just brought them up, and getting to what you were just describing of this population coding now, and thinking more in terms of even maybe that embodied idea of something ongoing that we're representing, and so the brain's not necessarily representing. But before we get there, the topographic map, I think, is a great place to kind of sit in this for a minute, because so we started with, we have this feeling of mental, physical, internal, external, and then external. And I think you talk about Plato and Aristotle and this kind of debate. Is it internal? Is it external? And then we get to dualism and Descartes. But really what we're trying to figure out is what's happening here. Is it where something was just all in our head from the beginning, and in terms of the way you describe the rats that are born, right? Is everything like that given to by God?
This is the argument that Busaki has joined. I mean, it's the inside out versus outside in approach. I mean,
I'm against the either or.
That is right. That's clearly right. So I think I may have already told you that Mary Peterson and myself and Drew Maurer and Sarah Burke in University of Florida, they were former students of Bruce McNaughton and Carol Barnes. We've been working for several years now, just slowly working working our way into trying to spell out a hybrid between the inside out and outside in approach to thinking about how the brain represents meaning. I mean, it's essentially the question we're talking about today. We have made very little progress so far.
I actually don't think we've talked about that yet, and that is really interesting. That's gonna have to. I need to like read up on that because I really feel like holding the paradox. That's how I say it philosophically. Is I think the hippocampus is like trying to help us do that, right? Because you can't go in either direction all the way. You need both. So how do we do it? And it's hard. But
how to think about the fact it can't be one or the other. It can't be an either or. Somehow
it can't
both.
be. Or it's both. It's a new way to have to process this. I think I think all this research that you're involved in, at least from my perspective, is showing us a way to do that. But it's very hard because you have everyone in their own camps trying to kind of prove, and that's part of the process itself. I don't want to get too distracted away from topographic maps yet because this word map is really important. And I think it can kind of like lead us because, and there's this very cool thing in case people don't know. Is it Penfield who came up with the sensory homunculus? Was it Penfield who kind of mapped it?
That's
a huge tongue.
That's the somatic sensory homunculus.
But basically what that's showing is that in the brain, most people's brains, there are certain areas that are associated with certain parts of the body, right? You can sort of, it's not like map is a tricky word. We could get into that, but more or less within the brain as it's developed with the body, there's a certain part that's got a lot of attention towards, for example, the hands or the lips or so.
Well, I mean, what we're finding out, and that was what the Kalbi Prize was about, was the face systems. It's usually more than one. I mean, the sensory homunculus that Penfield pointed out, would make you think that, there's this one place in the brain where the face is represented. Well, no, actually, there's about 7 or 8 face patches, it turns out, of increasing degrees of complexity, you might say, and increasing degrees of invariance. When you get to the sort of top of that hierarchy, you have a system that is representing a face, no matter which angle you're seeing it in, and so on. I mean, so but basically, yes, the brain has these three, and motor. I mean, the motor system's the same.
And that's so important what you just said, because I think even in a lot of ongoing neuroscientific study, it's still taught in the old way. Not in the way you just said, that there can be many different places where this is happening. But it doesn't change. That's the either or too. It doesn't change that actually there is associated regularity.
Right. That's the localization kind of argument, basically. Is the face system localized to one part of the brain? The answer is no. We now know it's distributed into several, but each of the patches may have quite a very specific function. There may be specialization within each of the face patches. It's not as if all these patches are equivalent, and they're all doing the same and collect.
Yeah. It's not like they're changing all the time. So I think to try to connect it to what we were talking about before, we're trying to understand how the things that we are aware of or experience are related to life and how the brain is doing it. So for example, with this map, you can kind of understand that certain sensory input with certain parts of the body, of course, like if you hurt the brain, for example, in that individual, then it's going to affect that part of their bodily experience of the world and movement.
Undoubtedly, exactly right. And all this,
that's the connection, right?
Stuff. Yeah, that's the connection. But things like that are all, relevant to this. And Ramachandran has done some really lovely work about this kind of stuff. Right. So what do we make of that, though? I mean, again, that's that's the sensory homunculus that Penfield, and by the way, he's part of the history lecture that I'm putting together. Because Penfield,
it even goes back to McGill too,
Exactly right. He was a critical link between the neurosurgeon who did the surgery on HM and Brenda Milner, who ended up studying HM, and Sue Corkin. Penfield was the critical link.
He brought in Milner, right? Or
he brought in Hebb, who brought in
Milner, right?
Then Milner, who brought in who sent Corkin to work with Milner
Tangled.
Penfield is part of the story, which is kind of cool. Yeah, right. So that was a little bit like the, image on the retina. I mean, we don't, yes, the brain is organized in that way that there are these topographic maps, so to speak. They are distorted. The visual system, there's even distortion within the visual system. There's, asymmetries and all kinds of eccentricities and so on. It's not a kind of a flat map, that accurately represents the 3D structure of what we seem to perceive as the Euclidean world. That's not the way exactly, but it's roughly topographical because that there's real computational advantages to that. And the same must be true in the somatosensory maps. There's got to be computational advantages to having, those things represented in neurons near each other. I mean, for start, this becomes a wiring issue. And I think I mentioned it, and I don't know that I mentioned it in the lectures, but I probably in the chapter that I didn't manage to get, the 1980 chapter. The computational advantages of having things close to each other involves this sort of minimum wiring constraint, which evolution presumably prefers. You want to have things that need to talk to each other as close to each other as possible. You also need to have long range communications because, et cetera, to the extent to which you can have nearby things, that are functionally near each other, that saves extra wires, which saves metabolism,
And by wire, you're talking kind of like Hebbian synaptic, or what do you mean by wiring?
That's like a separate issue. No, this is just an issue of development. I mean, when the brain is developing, I mean, it takes
so they're literally connected by synapses, or how do you?
It takes a lot of energy to make connections between neurons, and the greater the distance between two neurons that are meant to talk to each other, because they have some similar function, the more energy it takes. I'm really talking about
connection, the nearness in space.
Yeah, the nearness in space, is a big advantage from all other things being equal. It's a big advantage to have things near each other if they're doing something similar. That's why the absence of any topography in the hippocampus initially struck people as, this is so crazy. Basically, have the neurons that represent two places in the world that are really close to each other in the world, they may not be anywhere near each other in the hippocampus. They could be, it's random. It seems like, there's been some argument about that. But so the hippocampus was this non-topographical map. That's what made it so kind of cool initially in the context of what we knew about visual maps. It was something that, it's not only visual. It was known early on that it was more than just visual, but, most of the experiments, default to vision. I mean, the rat's moving around the world, it sees what's out there, blah, blah, blah. And yet the way the brain mapped it wasn't topographical. So, and
I think that's part of that either or, holding the paradox coolness of the hippocampus too, that everyone's having to deal with that. But this is very interesting because so this idea of topography is quite amazing, right? Like, this was an amazing thing to figure out, that within this organ in our body, probably different for everyone, but as you develop, probably you come with certain regularities that everyone shares, but as you develop, certain parts of your brain are going to correspond to certain parts of your movement and your sensation and the body parts, right? And that's fascinating and so cool. We thought of that as a map, right? That you can map this onto the brain. And this is where the representation gets confusing, because topography doesn't solve the problem of representation. It doesn't solve any of that stuff we were talking about. But it starts to seem like now we have a representation, but actually we've drawn a diagram, which is the representation of kind of being able to create another third thing, which is a kind of map of this part of the brain corresponds to this part of the body. But then, like we were saying, people start thinking there's a map in the brain, and this gets kind of confusing. Yeah.
Right, exactly. I mean, it solves no problem at all. I mean, it solves the mechanistic computational problem, clearly.
But not the meaning problem. That's how you put it in here.
But not the meaning and representational problem. Yeah. So, I mean, so a lot of the work that is being done is really focused on the mechanistic problem. I mean, how is the system doing, creating these maps, and how are these things used, and so on.
And how do we know it? Like, how is this experience that? We found that wonderful correspondence, and that tells us something, but to then think, oh, well, that's what's happening. That's how we have this little movie in our brain. No, it's too confusing, but we don't have this little.
We don't have that. And I don't think, quite honestly, I mean, I certainly don't have any really clever ideas about it yet. I don't know, this week there's going to be a visitor here who is from Israel, a guy, Yoram Bora, who collaborates with Edvard Moser and probably Margaret as well. And he's a former student of Sampolinsky. I can't remember Sampolinsky's first name. He's really one of the grandfathers of computational neuroscience, trying to sort of figure out how attractor networks and how all these things end up representing. I mean, that's really what they're trying to get at, but they're really working on the mechanistic issues. I mean, how does it do the job that it does? And they don't really, until you liquor them up a bit, they don't necessarily want to talk about the meaning question. I mean, how does this set of activities come to represent something in the way of meaning that thing?
It's interesting that you bring that up because, right, we're kind of jumping around, but we got to this idea of it not being a map in the brain. But for a while, we sort of thought, okay, there's like a little picture in the brain, and there's a topographic map, and there's an image, and so on. Now we still confuse all of these words. Even thinking about computational representation in the brain is I think, a similar mistake to thinking of maps in the brain. But it doesn't mean the word map or the word computation is wrong. It's just that we get confused about.
I don't think it touches the problem at all. So you get somebody like Tim Behrens, who's arguing that some kind of a geometric six-fold representation is the common code for the way the brain represents information. It's going beyond the, building off the grid cell notion, and how well the grid cell population tiles the whole environment. He's taken that idea and sort of said, well, you can find this kind of six-fold representational structure to the population code again, all over the brain. He's arguing, and I think I talked to John about this as well. And John, we also think that he's probably gone too far here. But even if that were the case, and you think about the grid cells, I mean, what is it about that particular computational structure that causes it to mean what it means? Or that we think it means, so to speak, what it means is something about the structure of the space that the animal is moving around in.
This is great because I think too that he's gone too far, so to speak, and trying to be so specific about the six-fold, so on and so forth. But what I like about his work in that Tolman and Eichenbaum machine is exactly that he puts Tolman and Eichenbaum together because, I mean, we kind of skipped over, so thinking about maps, and then I think in your lecture you go into sort of feature detection and contrast and Hubert and Wiesel and all this, and it's kind of moving more towards where we are now, population coding, right? Where you're looking at regularities and so on and so forth. And I bring that up, but then also the Tolman Eichenbaum, I would like to hear your perspective about, do those not fit together? Eichenbaum's idea and.
Well, what's the idea? What do you see as the core idea in the Tolman Eichenbaum machine? What is it doing?
Well, I mean, I think I would need to think about that a little bit more, but I'll tell you what I'm trying to get at here in terms of this conversation. So Tolman is associated with the cognitive map, for example, or the idea that when a rat is moving through its spatial location, that's also a kind of knowledge, so to speak, and that we could map it. I'm now giving him words he doesn't necessarily use, but in the same way we draw these little homunculi kind of things, we could probably do that with certain individuals or certain rats in terms of how they're moving through space and how certain parts of whatever is happening in the hippocampus is happening, right?
Yep. Yeah,
and it gets way too confusing. I'm not saying it's a six-fold this and that and that.
No,
but
sure. Tolman didn't care about that.
No, he doesn't care.
He was not into the brain. Yeah. Tolman was just talking about the cognitive structure.
But that moving through a space is a kind of knowledge, right? I just think that's an obvious kind of thing that we can say is.
The knowledge that Tolman claimed was the knowledge, the kind of what leads to what knowledge. I mean, what Tolman claimed was that the animals form a kind of a mental map, a map of the world, something like a map of the world in their head.
Something like parts of the brain being associated with regularities in the way we described with the topographic map, but not no hard and fixed as that, but something like that going on.
You pushed him, he might have said that, but he really didn't ever talk about the brain.
Yeah, but that same kind of idea, right? That as you develop, of course, you kind of associate certain regularities with certain whatever functions. Yeah,
that would be the modern way of talking about it. So that's the Tolman part of it. Tolman talked about the representations that our brains must be forming and the fact that they can be used as in predictive mode. That
good way to say it. Yeah,
and that basically they tell the animal, if I do this, then the following is going to happen. He he connected all of those dots cognitively.
Right, which is great because that's kind of like a map, right? Because you use it in order to sort of infer where you're going to go.
That's why O'Keefe and I built on that. I mean,
exactly. And that goes into the beautiful book, which we've discussed, Hippocampus as a cognitive map.
So now tell me about the
Eichenbaum.
Eichenbaum part of it.
Okay, well, this is what I think I'm missing something because I feel like there's a lot of controversy or fighting about something. I don't know that I really understand Eichenbaum totally with this idea of association. I guess what I think is kind of clear and what I like about the Tolman Eichenbaum is that we could probably find some way, I don't think anyone's found it, but to understand that the same way that we study how, for example, we move through physical spaces, and that all of this that we've been talking about, there are regularities and we could probably find maps. And I mean that external maps that we draw or computational models that we make is what I mean by representation. That we could also do that with other spaces because we're setting what a space is. You set the little room for the rat, but you could also set a little knowledge space, so to speak. And for me, it's still all regularities that we've learned. And you're still moving through a space in a similar way. I don't mean that like the way we move through a room and the way we move through a book are going to look the same, but there's probably some kind of pattern or regularity towards how we could understand those processes that is the same. That's how I see that connection being made in a nice way. But I could be wrong. I mean, I don't understand what Eichenbaum is so controversial about.
Well, I think the controversy comes from the fact that, this idea is built on the kind of Eichenbaum and Cohen, really, notion of relational memory, and the brain is coding these relations, and the hippocampus in particular is a relational memory device.
So that would be this either or thing, right? So that then precludes all the other stuff we were talking about. Is that
not really, because since they may think it does that, but
I don't think it does. But it seems like people take it that way, and then I can understand the controversy, I guess.
I don't think the idea is so much controversial as vacuous.
Okay, well, what is the idea because I think I'm missing what that is.
The vacuous part is that Eichenbaum talked about this as one piece of the kind of brain's function, this relational device, right? The hippocampus is specialized to kind of create these relations, and it does it for space and for all these other things as well, right? That's the point you're making. The problem is everything the brain does, not just the hippocampus, everything the brain does is relation. There is no non-relational part of the brain. It does not exist. It's a nonsense idea. Every neuron gets inputs and is relating inputs from multiple sources. There is nothing that is non-relational. It simply is not a useful explanatory idea. So in my view, and also John and I are very strongly in agreement on this. There's just it doesn't help you. Everything is related.
So that he's saying that. So is he saying the hippocampus's main purpose is to relate?
Yeah, yes, uniquely so.
Okay.
And there are other parts of the brain don't have this kind of special, ability to relate things to each other. Is the core of the Eichenbaum-Cohen relational idea, and that is built into this Tolman-Eichenbaum approach. That you have this unique relational device. But that's crazy. The whole brain is a relational device. Everything the brain does is relational.
See, that I didn't get at all, that it had to be a device that's relational. To me, it was much more of a theoretical, very much grounded in kind of the things you start with in your book, with space and how we understand space. And
as you said yourself, they're talking about it as an association machine. The Tolman-Eichenbaum machine is a machine that makes associations, but that's an association is just another word for a relation. And the brain is in the business of everything is associative. There used to be in psychology this kind of big distinction between associative and non-associative learning, as if there could be such a thing as non-associative learning, right?
I think they're still talked about as if associative. I mean, people don't talk the way I agree with what you're saying, but this is confusing because when in all brain research we don't talk about the brain as being like that.
Yeah, no, that's the reason why there's this controversy, that some people are kind of taken up by this idea. Oh, that's a really cool idea. You got this special relational associative device, the Tolman Eichenbaum machine, blah, 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 without actually kind of digging deeper and, trying to say, well, okay, what's the rest of the brain doing? Is it doing non-associative things? What does that mean? Every part of the brain is doing associative things. There is no distinction. Otherwise, the brain would just be a bunch of isolated wires, going
Yeah,
from in
yeah.
output. There'd be nothing else going on.
I agree, but we talk about associative memory as if it's one kind of memory. We don't talk about all memory as
It's not.
associative,
What I'm
even though
trying
it
to
is.
what I'm trying to tell you is that so-called non-associative memory, which were things like habituation, sensitization, they're not non-associative.
I agree
Habitu-
100%, but it's not the way you're taught that,
No,
So
no, no,
I can
no,
just imagine a lot of people aren't even understanding
no. You're
that
absolutely right.
that's what he's saying,
You're
because
absolutely right that the objection I'm making is not one that is widely kind of mooted in the in the literature at this point. But sooner or later, people are going to realize that it's a vacuous, that this idea, I think they're going to realize that this is a vacuous idea. It doesn't get you anywhere,
I
basically.
don't think it's vacuous, but I think it's not like an answer. For me, it's like a tool to rethink some of these things. Even, Tolving, I love Tolving and these different kinds of memories, but
Right.
we do need to do some rethinking about how we categorize all of these memories and things. And I
Absolutely.
guess like being a little bit kind of, not really I have studied Eichenbaum and all this from an angle from which I want to see things, right?
Yeah, yeah.
Not, and everyone's doing that. So I can see how this gets incredibly confusing, but to just not try to stick it to like a theory. I think what's interesting is like, for me, and you might really disagree with this, is like, that doesn't seem so far from a cognitive map in the Tolman sense of like, I wouldn't say, for example, that, okay, we're just because we can understand that cognition is, that when we're moving through a space, that is also a kind of knowledge, then we just say, oh, okay, everything is movement and everything is knowledge. I mean, we could also kind of do that too, right? And that would be vacuous. But instead, if you really look at what's being said there and you start to understand, there's actually very big, huge differences in terms of these parts of the brain, or even if not, right? Even if some other part of the brain could become something like the hippocampus, it would still be interesting that the brain itself, in some way,
Yeah.
is developing some kind of regularity that can then be used in many different situations to,
Yeah, I
know.
believe, however, that every part of the brain is doing what you're just saying. That is not unique to any particular system. That's just the way the brain works. Every part of the brain is engaged in extracting the regularities from the input patterns that it receives, basically. And those input patterns necessarily include relational information. They have to. They always do. They're not about like one point in space. They're always about things that involve relations. So my problem with that approach is that it doesn't seem to me to add any useful explanatory power to any other story. It's basically gets back to everything is associative. Everything is associative, and that again, the philosophers were okay with that idea. That the brain works on the basis of associations. That's what it does, and it's not this part of the brain that works on the basis of associations and extraction of statistical regularities and so on. It's every part of the brain is doing exactly that.
That's kind of incredible. I mean, I think if you take, we don't have time to go into all of your work, but the things we've talked about in other discussions together, and the reason that I believe this whole kind of Tolman through the Mosers, all the stuff that you're now celebrating there, I think in Trondheim, I think this is incredibly important because it does show us something that does tell us something about what we were trying to talk about how we can be in the world and experiencing the world, and that's like a continuous thing.
It does. Absolutely it does, but we're back to the kind of inside out versus outside in.
But why does it have to be either or? I mean,
and what is the magic sauce that is going to help us understand, how both of them, both the internal structure like that shows up at day 10, independent of experience. And the actual experience that the organism has, which actually then refines the shape of the torus and refines, and then the grid cells emerge after the torus.
Maybe it is something like the association, though. And I don't mean that in a vacuous way, but I mean it connected to all the research you guys are doing. If you do start to think of the brain in that way,
it is.
and you think of it in that immediate sense you brought up at the beginning, actually we get somewhere really new and beautiful.
I hope you're right.
But the problem is, to go back to representations, is we can't get rid of that trying to find it in the brain or find it in the world.
Right.
Instead of understanding association as a process that isn't represented in the brain or the world, but we can represent with the books we write and the computational models we make and the images we draw.
And I mean, the notion of a representation in the brain may just be a slice through a moment in time, and that the representation is really some combination of the structure of the brain and the structure of the world and the inputs from the world to the brain and the tight coupling between those two. And the kind of compromise between those either or positions is figuring out how that coupling works, basically. And when you say, that this activity in the brain represents X about the world, then something about the world is, part of that story. It has helped create that, that set of brain activities, either phylogenetically or ontogenetically. And, the answer is going to be found somehow in the interactive kind of re-entrant, recursive sort of language that the brain uses, to sort of interact with the world. And that's kind of what we're working on and trying to figure this out, is the middle ground has to be, somewhere between those two. And how does a particular network come to have the meaning that it has? We're no longer talking about patches or maps, but, an entire network or population of cells. How do they come to mean what they mean, and how do they come to have the power they have to generate behavior, so to speak? And it's got to be some interaction between what's out there in the world and the experience the organism has, and the kind of the pre-wired structure of the system, which was pre-wired because of millions of years of evolution, that built it that way because it actually worked in the world. And so it's got to be connected to the world in that way. Another free device, basically. The point I was trying to make about Tolman and Eichenbaum was that no matter how you think about this, it's going to be an associative device of some kind, right? And so,
that might be the contribution that I'm thinking he's bringing, because I don't think we talk about it like that, and I don't think it's actually vacuous to talk about it like that. If you bracket it in the way we're talking about it, if you just say, okay, the hippocampus is this little device in the brain that does this, okay, and it does it through this and this and this, okay, then we're getting that's not going to help us.
I'm open to that possibility.
Yeah. But I do see a way that those things there could be helping each other. This tradition that it's, so important to me that you guys all there are doing. And what he was trying to say, sometimes in probably almost a cartoonish sense, about there being a way in which this is happening in all these different contexts,
That's the question. Yeah. And how does that work? But you know what?
What?
You're gonna know we've run out of time.
I know. We have to go.
For me, I have to quit now. So
yeah, me too.
We can pick this up again, next month, or we can set up another talk song.
Yeah. Will you can I read your talk that you're going to give there? Maybe.
I will.
Or some part of it.
This history thing.
Yeah. Or send me some of the stuff you were just talking about, the hybrid stuff too.
That's not ready. That's not ready.
Okay. Well, then maybe your talk that you or something.
Talk, which is really a different thing. It's just interesting history. I can send you once I have the PowerPoint finished, then I can send you this. Then I can, and I think a lot of it on the slides. I mean, some of it won't be, but most of the story will be on the slides.
Okay, that would be great.
Yeah.
Okay, let's do that.
Done with it. I won't be done with it for another week or so, but when I'm done with it, I can send it to you. And
okay, I'm in research mode, so I'm finally staying still. So when you get back and settled, just let me know. We can.
I'm back 2nd of October, so we can set something up for the middle of October.
Yeah, around in
months
October.
from
So
now.
that
Okay.
would be perfect. Yep, sounds
Right.
good.
It was
Have
fun.
fun there. Yeah, always fun.
Send me the paper